We're going to take a look at worksheet number 20, specifically questions 6, 8, 9, 11, and 13. We'll start with number 6 here. It says the work function of a particular metal is 2.50 eV, 0 electron volts. Will visible light of wavelength 5.5 times 10 to the 7 cause electrons to be emitted? Photoelectrons, electrons ejected in the photoelectric effect, to be emitted here. So what do we got to do here? In order to get electrons ejected, you have to be above the threshold frequency. You have to be above the work function. You have to be below the threshold wavelength. So we've got a certain work function given to us here. We've got a wavelength. We want to see if we're either above the work function or below the threshold wavelength. I don't really care which way you do it. Compare the wavelengths, compare the work function. Doesn't really matter. You're going to get the same answer, the same conclusion in both cases. Let's do it both ways, just to demonstrate how we would do it both ways, and then we'll see how many of you guys did it one way, how many did it the other way. Here's our work function. Let's calculate the energy of this photon right now. The energy of this photon is hc over lambda. Now, what value of Planck's constant am I going to use? 6.63 times 10 to the minus 34 joules seconds, or 4.14 times 10 to the negative 15 eV seconds? Probably the 4.14 value. Although, we said that there's a few situations, not very many, but a few situations in which we must use joules. This is not one of them. You can use electron volts here. But if it confuses you as to when you can use joules and when you can't, then just always use, when you can use electron volts and when you can't, then you should always use joules because joules always work for you, right? Now, this is one of those situations where you can use electron volts. If you recognize that, go ahead and do it. But if you don't, then convert to joules. If you do that, however, you got to make sure you're consistent through the question, so you'd want to make the work function into joules as well to make that comparison. I'm going to leave it in electron volts because I can. Now, when I calculate that energy in electron volts, Justin, do you have the answer for that? Yeah? 2.5? Not 2.5. 2.26, thank you. 2.26 electron volts. So my energy is 2.226. My work function is 2.50. 2.26 is below the work function. That means the electrons will not be ejected. So the answer to that is no. Now the other way you can tackle this, though, is to find the threshold wavelength from the work function. We'd say E is equal to hc over lambda max. Solve for lambda max. It's hc over the work function. Once again, I'm going to stick with the electron volts here. You can use joules. You can always use joules. But if you do that, it means converting this to joules as well. So we're going to say 4.14 times 10 to the minus 15 times 3 times 10 to the 8. Divided by 2.5 gives me 4.97 times 10 to the negative 5 meters. So we would say in the first case that since the energy of the photon is less than the work function, no, electrons will not be ejected. In the second case, we would say that since lambda is greater than lambda max, no, electrons will not be ejected. You cannot be below the threshold frequency, and get electrons ejected. You cannot be below the work function and get electrons ejected. You cannot be above the maximum wavelength and get electrons ejected. Does that make sense? How many people did it the blue way here? E equals hc over lambda and then compared the energies. Okay, how many people did it the green way and compared calculated the maximum wavelength and compared wavelengths together? Okay. I don't know. I don't know which way I like better. I think I might like the blue way better. But that's just a preference thing. One's not better than the other, really. All right, next question we want to go over is number 8. And number 8 says calculate the maximum photoelectron kinetic energy emitted from a metal whose work function is 1.5 eV. And when the metal is illuminated by visible light with a wavelength of 700 nanometers, we know we want to convert that for sure. Maybe want to convert this. We'll deal with that. Yep. No, a photoelectron is just an electron that's ejected in the photoelectric effect. It's exactly the same thing. It's any other electron. I don't know if you guys noticed, I was counting to 5 on my hand. The little 5-second rule. Remember the 5-second rule? Can't come up with an equation for one of these photoelectric effect problems. You should use HF is equal to EK max plus W. By the way, that comes from the law of conservation of energy, right? HF is equal to EK max plus W. We want to know that because it doesn't appear on our data sheet, and we're going to have to, if we want to use this, we want to have to derive, or we want to be able to derive that equation. So HF is the initial energy of the photon, EK max is the final energy of the electron, and W is the energy that we used up in the process of ejecting that electron. Now, the reason this is so versatile is because we can make a lot of substitutions in here. We don't know what the frequency is, but that's okay because we know what the wavelength is, and we can make a substitution there. EK we're looking for, and the work function we already have here. So let's sub some numbers in here. Can we use the electron volts here? Yeah, we can actually. There's 2 situations that we've learned so far that you can't use the electron volts. Anybody remember what they are? Shelly? Right. When you're using 1 FMV squared or QV. 1 FMV squared or QV. Here we've got kinetic energy, but I'm not replacing EK with 1 FMV squared or QV. Does that make sense? So EK can be in EVs, electron volts all you want, but 1/2 MV squared or QV, you can't use electron volts for those. So I can use electron volts here. I don't have to. If you're not comfortable with that, then convert. If you're not sure, then use joules because it always works. It just ends up being a little bit more work sometimes. I'm going to use the 4.14 value because I can. C is 3 times 10 to the 8, of course. The wavelength here is 700 nanometers. That's 700 times 10 to the minus 9, not 7 times 10 to the minus 9. We're looking for EK. And the work function is 1.50 eV. If you had to use the 6.63 value right here, then you would have just had to make sure that you converted that to joules, which isn't that hard, but you just got to be consistent, remember. The left-hand side works out to be 1.7743 eV. And of course, we're going to take the 1.5 over by subtracting. We end up with 0.274. So this question clearly has an electron being ejected. We want to find the kinetic energy of that electron. And when we have electrons ejected, we often go to this equation. HF is equal to EK max plus W. EK is the kinetic energy of that electron that's been ejected, and it works out to be 0.274. Can you tell me why this equation wouldn't work if an electron was not ejected? What would you get for EK if the electron was not actually being ejected?
A negative value.
Yes, it would be a negative value, and that doesn't make any physical sense, does it? Right? If you end up getting a negative value, then you know you've either made a mistake or you've read the question wrong somehow that an electron is not being ejected. Okay? And this is the initial energy. This is the final energy. Sorry, this is the energy that's used up. If the energy used up is more than the initial energy, then we got a problem. Kinetic energy is going to be negative, and that doesn't work. Yep. What if it was the same thing? You got to be, that's a good question. I guess you'd say in that case just an electron has been ejected, but just barely. It doesn't go anywhere. It doesn't have any kinetic energy. What's the next question? Number 9 that we wanted to go over. It says calculate the maximum kinetic energy again. This is a good question. From a metal whose work function is 3 electron volts, if the metal is illuminated by visible light, 400 nanometers to 700 nanometers. If you want to eject an electron with the most energy, you need to use a photon with the most energy. The photon with the most energy is the photon with the blank wavelength. Smallest wavelength, the least wavelength. So we want to use this 400 nanometers. The 700 is completely irrelevant. That's going to give us a small energy, and of course you're not going to get the most kinetic energy from an electron with the smallest energy photon. Right? You want to, you're in a smash-up derby, a demolition derby with cars, and you want to provide them. You want to provide the most energy to that car over there by hitting it. Well, you don't hit it with a car that doesn't have hardly any energy. You hit it with a car that has a lot of energy. Okay? How do you transfer a lot of energy to another vehicle? Have a lot of energy yourself. So if we want to have a lot of energy going to this electron, then we need to have a lot of energy coming from the photon that provides it. All right, so that's the wavelength we use. What equation do we use? What equation are we going to use to find the maximum kinetic energy? Yeah, I just counted to 5. Okay, Kessler tells me that after 5, we're going to use HF is equal to EK max plus W. Remember that, like, if we're wrong, like if we just happen to miss the equation, that's okay. We're just going to use this, and we're not going to get an answer, or we're going to get a negative value for EK or something like that. Like, but odds are, if you haven't figured out what equation to use in 5 seconds or so, then this is the one you're going to use. Now we're going to replace this with hc over lambda, because we've got the wavelength. And now the question becomes like the last one, right? Now it's virtually identical to the last one, except that in this one we have different numbers. hc over lambda, EK, subtract, take the W over by subtracting. And when we solve for EK there, using the value of 400 nanometers for the wavelength, we get an EK equal to 0.105 EVs. Anybody do this in joules? Yeah? Did you get 1.68 times 10 to the minus 20? You got what? 1.73 times 10 to the negative 20? Did you use 700 nanometers?
I'm not sure whether you use another two constants. I'm not sure.
Which one? Okay, fair enough then. If, just remember that if you're using electron volts here, you got to use electron volts here. So this is 3 electron volts. This would be 4.14 times 10 to the minus 15. If you do convert this to joules, 3 electron volts would be 4.8 times 10 to the minus 19 joules. Then you use 6.63 times 10 to the minus 34 joule seconds. Okay. Take a peek at it and get the right answer. If you can't get the right answer, then let me know so I can help you out with it, all right? Of the answers, you mean?
I think so.
No.
Or did I just not?
Yeah, I think you might have just copied it wrong or something. 1.68 times 10 to the minus 20. Might have been looking at a different question or something.
I'll look back.
Okay, yeah. All right, number 11. What's the maximum speed of an electron, or Kessler, a photoelectron? What's a photoelectron? Yeah, it's the same thing. Just an electron that's ejected. Emitted from a metal whose threshold frequency is this value. The metal is illuminated by light of frequency 2.5 times 10 to the 15 hertz. We have to assume that an electron has been ejected by the wording of this question, right? Anybody have an equation that we can use for this? I've gotten to at least 10. Nobody's given me an equation yet, so which one are we going to go with, Kessler? Yep. Can't come up with one in 10 seconds, and we're definitely going to go with this. Okay, I got frequency. Good. I don't have kinetic energy. What am I going to do? Yeah, let's replace it with 1/2 mv squared since we're looking for maximum speed. Oh, we don't have the work function either. What are we going to replace that with? HF0, right? So be careful. The difference between frequency and threshold frequency. Frequency is the actual frequency that we have. Threshold frequency is the minimum possible frequency. Now, what do you want to use here, joules or electron volts, or does it matter? Joules always works, right? If in doubt, go with joules. Do we have to use joules? Yes, we do. How come? Because we've got 1/2 mv squared. Okay? If confused about that again, like when you have to, when you don't have to, just use joules every time. This means a little bit of extra work sometimes. So 6.63 joules seconds has a frequency of 2.5 times 10 to the 15. Do not use the 2.0. Okay, that's the threshold frequency. What's the mass that we use? Yeah, we only got two things here, right? We got a photon, we've got an electron. Okay, photons don't have any mass, so it's going to have to be the mass of the electron that's ejected. .63 again, got to be consistent in a question, times the threshold frequency of 2 times 10 to the 15 hertz. So let's calculate the left side, this number right here. Calculate this, and then take this number over by subtracting. That's going to give me, take that over by subtracting, multiply it by 2, divide by 9.11, and guess what do I end up with there? 10 to the, oh, no, that's not right. You got to square root that, right? Hold on, though. No, I'm glad you said that. 7.27 times 10 to the 11, he said. And I was writing that down blindly, and then he said 10 to the 11, and I'm like, well, that can't be right. Why could that not be right? Because it's faster than the speed of light. So in all likelihood, when you get a 10 to the 11, it means you've forgotten to square root it. So if you square root 7.27 times 10 to the 11, what do you end up getting now? 8.53 times 10 to the 5. And 10 to the 5 is a much better speed for a charged particle. It's pretty much bang in the middle there of the range that we would expect to see, 10 to the 5 meters per second. And 13, when 230 nanometer light falls on a metal, the current through a photoelectric circuit is brought to 0 at a reverse voltage of 1.64. Man, that's kind of crazy wording, eh? The current is brought to 0 at that reverse voltage. Like, what are we saying here? What am I saying that we just did here? The current is brought to 0. The electrons that were moving have stopped moving. The reverse voltage or the reverse potential difference is 1.64. So if we applied a potential difference of 1.64 to stop the electrons, then what have we got here? What is this 1.64? What variable would we call that? It's a stopping potential, right? The potential difference required to stop the electrons once they've been ejected. The current is brought to 0. The electrons have stopped. This is the potential difference required to do that. That's defined as the stopping potential. We've got a wavelength here, 230 times 10 to the minus 9 meters. And we want to find the threshold frequency. Anybody got an equation? I'm waiting. I don't have one, so what are we going to go with? Spencer, which one are we going to go with if we don't have an equation after 20 seconds? Okay, so we don't have F, so let's replace HF with HC over lambda. We don't have EK, so let's replace it with QV stop. We don't have W, so let's replace it with H times the threshold frequency. Do you see how even though that equation certainly didn't look like it fit the givens, we weren't sure which one to use, so we went with it, and it works. Joules, electron volts, does it matter? Adam, does it matter here?
No.
No, you use electron volts if you want?
Oh, wait, no, you can't.
Well, how come? Why can't we use the electron volts? Matt, help him out there? Because we're using QV stop, good. Yeah, as soon as we introduce QV stop or 1 FMV squared into the equation, we can't use the electron volts. You got to use joules. If in doubt, Adam, if in doubt, just go joules. It just means that sometimes you'll have to do a conversion in there that you wouldn't otherwise have to do. Okay, let's sub our numbers in. 6.63 times 10 to the minus 34 times 3 times 10 to the 8. Divided by the wavelength, which is 230 nanometers, or 230 times 10 to the minus 9 meters. What Q do we use here? Amanda, what Q do we use? What value of Q do we use here? What is it in this whole photoelectric effect that has charge? Quinn? Yeah, it's the electron. So the charge, we use the charge of an electron there. Right? Just like we use the mass of the electron, we use the charge. 6.63 times 10 to the minus 34 times the threshold frequency. Oh, wait. Wait, we have the stopping potential. It is 1.64 plus 6.63 times the threshold frequency. So get this number. Get this number. Take it over by subtracting, yeah? And then we take the 6.63 over by division, yeah? And we end up with, in number 13 for the threshold frequency, what is it, 9.09 times 10 to the 14 hertz. Okay, so what kind of EMR, 9.09 times 10 to the 14 hertz, what kind of EMR would you need to use to cause the electrons to be ejected here? Ultraviolet, yeah. Visible light goes from 4 to 7.5 times 10 to the 14. So it's really close to visible light, but we still classify it as ultraviolet.